Hey everyone, welcome back to my podcast, Anatomy and Physiology Bit by Bit. This is your host, Dr. Steve Sullivan, and as most of you know by now, I'm coming to you from Bucks County, Pennsylvania, which is just outside of Philadelphia. I've been teaching A&P at Bucks County Community College since 2002, so now we're going on my 23rd year of teaching this class. So this episode, we're going to continue on with the endocrine system, and we're specifically going to get into the difference between how water-soluble and lipid-soluble hormones have to have their action. So we know that it's difficult for lipid-soluble hormones to be transported in the blood plasma because they're not water-soluble, and the blood plasma is mostly water. But also, it's difficult for water-soluble hormones to get into a cell because the plasma membrane is mostly lipids. So we have a little bit of a conundrum there. While it's easy for water-soluble hormones to get to their target cells because of the blood plasma being mostly water, it's difficult for them to get into their target cells because of the plasma membrane being mostly lipid. Conversely, it's difficult for lipid-soluble hormones to get to their target cells because lipids do not dissolve in blood plasma, which is mostly water, but it's easy for lipid-soluble hormones to get into their target cells because they can diffuse right through the lipid bilayer of the plasma membrane. So this is our little dilemma here, and we're going to talk in this episode about what these two different classes of hormones do to have their action on their target cells. Before we get into the content today, I do want to start by addressing a question that I received from a listener. And I want to remind you all, feel free to email me questions. So if you have a question about an episode, if something popped into your head, or you have a question about anything A&P related or clinically, send me a question. You can email me at minus55media@gmail.com. So it's minus55media@gmail.com. And send me your questions. Please don't send me specific clinical questions about yourself. I'm not going to answer questions that your doctors should be answering. But if you have a general question about A&P or something that I cover or talk about in the episodes, feel free and I will try to answer them in another episode. The question I got this past week was related to our sensation episodes, and specifically hearing. This question came from a listener whose name is Marissa, and Marissa is outside of St. Louis, Missouri in the United States. And Marissa said that she was at a doctor's appointment, and they were doing some tests, and they did the typical tests where the doctor asked her to stick her tongue out and follow her finger with her eyes only while she made the H pattern in the air. These are typical cranial nerve tests. And what she asked was, why did the doctor put a tuning fork on top of her head? That's a really good question. So if the doctor takes a tuning fork and taps it and then puts the stem of it on top of your head, what they're doing is they are testing cranial nerve 8, specifically the cochlear branch of cranial nerve 8, which is the vestibulocochlear nerve. It's a hearing test, and it is called the Weber-Reney test. What they're doing is they're trying to see if vibrating your skull sounds louder in one ear than the other. So here's what's happening here. With this test, they're trying to differentiate whether a hearing loss is because there's a hard time for the sound waves getting to the tympanic membrane, to the auditory ossicles, and into the cochlea, versus a hearing loss that is caused by a blockage somewhere in the cranial nerve, the cochlear branch of cranial nerve 8, or cochlear nerve, as you might call it. If there's some kind of disruption of the nerve signals getting to the brain. That's what they're looking for. So it is the difference between what we call a conduction loss, which means the sound waves are not getting to the cochlea, or a neural loss, which means that the nerve signals are not getting to the brain. Here's the difference between those two. Think about when you talk, your vocal cords are vibrating, and they're vibrating the air molecules that are coming out of your lungs and out of your mouth. They're also vibrating your own bones, like your skull. And those vibrations of your skull are also creating waves in endolymph in your cochlea. So there are two ways that you are stimulating your own nerve signals that are going to your brain to perceive hearing. Think about any time you've ever heard your voice recorded and you think to yourself, that doesn't sound like me, that's not what I sound like. It actually is what you sound like to other people. The difference is when other people hear your voice, they're only hearing your voice as it creates sound waves through the air. But when you perceive your voice, you're perceiving a combination of the sound waves you're creating in the air getting to your own ears from the outside and the vibrations you're creating inside your own skull, making waves of endolymph in the cochlea. So your brain is perceiving both of those data sets and then creating a perception of sound. And so what you perceive the sound of your voice to be is different than what other people perceive the sound of your voice. It's interesting. If you've ever watched a show like American Idol or something like that, and you have these contestants who come up and they think that they're amazing singers, and then everyone else hears them and thinks, not so much, and you're like, how could they have thought that they were better than they are? It's because they're not hearing themselves the same way everyone else is, right? Your voice doesn't sound to you what it sounds like to other people. All right, that aside, imagine that someone's saying something you don't want to hear, and you plug your ears and you go, la, 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 I can't hear you because you don't want to hear what they're saying. What you're doing by plugging your ears, you're blocking their sound waves, but not entirely. But also then by making your own sounds, you're flooding your cochlear nerves with the vibrations of your own voice in your head, so that now you can't hear what they're saying. Notice how much louder your voice sounds when you plug your ears than when you don't. So we have this perception that the sound is louder when it's only coming from those internal vibrations. So here's what that tuning fork on your head is for. So what the practitioner is going to do, tap the tuning fork, vibrate the stem, put the stem on top of your head. Now the tuning fork's not making enough vibrations in the air for you to hear it, but the stem is vibrating your skull enough for you to perceive the sound. And what they're going to ask you is, does this sound louder in one ear than it does in the other? And if you say yes, that means one of two things. That means that either you have a neural loss, which means there's no nerve signals getting to your brain from the ear it's quieter in, or you have a conduction loss, which means there's something blocking the vibrations of sound from the air in the ear that it sounds louder in. So that's phase one of this test. Now we have to figure out which it is. So we take that tuning fork and we hit it again, and we put the stem on your mastoid process of your temporal bone behind your ear and say, can you hear that? And if they say yes, then we know that that nerve is working on that side. So I would say to the person, okay, well, tell me when you can no longer hear that. And when they say I can't hear it anymore, that means the stem of the tuning fork is no longer vibrating strong enough to vibrate your skull through your mastoid process. So then I take the tines of the tuning fork without hitting it again and put it right next to their ear because it's still enough to vibrate the air to create sound waves and say, can you hear it now? And if they say yes, then they are probably fine in that ear. They can hear it through the bone conduction and they can hear it through the air conduction. Now they should be able to hear it for about twice as long through the air as they can through the bones. So if that's the case, that ear is fine. So then I go to the other side and I do the same thing. And I hit the tuning fork and I put it on the mastoid process and I say, can you hear that? Now, if they say, no, I can't hear anything, then I'm going to assume that there might be some kind of blockage in the cochlear nerve. And we need to look into that as a possible neural loss of hearing. If they say yes, I can hear it, and then I say, tell me when you can't hear it anymore, and they say, okay, I can't hear it anymore, and I put the tines of the tuning fork next to their ear, and I say, can you hear this? And they say no, then I think there's a conduction loss there. The sound waves through the air are not getting to the cochlea for some reason because they've lost the air conduction stimulus to create nerve signals going to the auditory center of the brain. So this is a cranial nerve test. So it should be part of a standard neurological exam. This is called the Weber-Rinne, R-I-N-N-E test. And I learned about it when I was in school. We did it when I was a student as part of our typical cranial nerve assessment labs and learning how to do cranial nerve assessments and full neurological examinations on patients. We did the Weber-Rinne test. So if you're wondering why a tuning fork was placed on top of your head and it seemed kind of weird, it's not. It's just a cochlear nerve test. Now, don't forget, there's another branch of the vestibulocochlear nerve, cranial nerve 8, that is called the vestibular branch, and that is for balance and equilibrium. So this one you can test in entirely different ways, and I do think that we talked about this in the equilibrium episode in terms of the doll's eye test, which is an interesting one. And there's a lot more for that. But thank you for your question, Marissa. I really appreciate you reaching out. Everyone else, please don't be shy. Reach out. -55media@gmail.com. I will put it in the show notes so that you can reach out to me. I like answering questions. I would love for this to be a regular part of the episode. I do think that sometimes people are a little shy about reaching out, but feel free. I'm here. That's what I want to do. So thank you again, Marissa. I appreciate your question. Let's get into hormones now. All right, let's get into the mechanism of action of the classes of hormones. Specifically, we're going to talk about lipid-soluble hormones and water-soluble hormones. We're going to start with lipid-soluble hormones because it's kind of the simpler version because lipid-soluble hormones can dissolve right through the phospholipid bilayer of the plasma membrane and get into their cells. Now, these lipid-soluble hormones can get into any cell they want or any cell they come in contact with because they're lipid-soluble, so they go right into the cell. Now, the difference is, does that cell have a receptor for that hormone? That's what's going to make it a target cell. So if there's no receptor inside, then big deal. Nothing really happens. But if there's a receptor inside for that particular hormone, then we're going to have some action. So remember that lipid-soluble is also called hydrophobic. And these hormones are the steroid hormones and thyroid hormone. Again, they can easily pass through the lipid bilayer of the plasma membrane and get right into the cytosol. And the goal is for that hormone to contact the cell's DNA on a target gene and either activate it or deactivate it. Now recall that genes code for the synthesis of proteins, which may be metabolic enzymes, they could be other hormones, they could be receptors, they could be lots of things, right? So all of the different proteins that our bodies utilize are synthesized by cells, and the DNA has the code on it to tell the ribosomes which amino acids go where in order to make a particular peptide so that we can have the right protein. So any of those proteins could be functional in these different ways. So a lot of times we use the term various metabolic reactions. That's the result of a hormone because we're talking about hormones in general, not specifically. So we don't know what their various metabolic reactions might be. But we're going to target a gene on the DNA and either activate it or deactivate it, right? So it's just as important to tell a cell to not do something as it is to tell a cell to do something. So each hormone is going to have its effect by stimulating or inhibiting its target cell's metabolic activity. So let's break the lipid-soluble hormones down into subclasses. So the receptors for glucocorticoid hormones, which are the hormones that come from the adrenal cortex, and we will talk about the specific endocrine glands and the principal hormones of our bodies in subsequent episodes. But the adrenal cortex, the outer shell of the adrenal gland, and the adrenal glands are just above your kidneys. So sometimes they're also called the suprarenal glands because they sit just superior, resting on the superior border of the kidney. So those glands have a distinct difference between the center of the gland and the outer shell of the gland. So the outer shell of the gland we call the adrenal cortex, and the center we call the adrenal medulla. The glucocorticoid hormones, which are lipid soluble, they're hydrophobic hormones, they come from the adrenal cortex. That's why they're called corticoids. They're called glucocorticoids because they tend to influence glucose metabolism. So the receptors for the glucocorticoid hormones from the adrenal cortex are in the cytoplasm. These hormones bind to their receptors, and the resultant complex is transported into the cell's nucleus, where it finds its target gene on the DNA. So the receptor for glucocorticoids is not in the nucleus at the DNA's gene. The receptor is actually in the cytoplasm, and then, bound to the receptor, the hormone then goes into the nucleus. Now, the receptors for steroid hormones like testosterone, progesterone, estrogen, those hormones have their receptors in the nucleus. So they go right into the nucleus. They don't have to bind to a receptor in the cytoplasm. They bind to a receptor in the nucleus and then reach their target gene on the DNA.
You buy a pair of socks, that's 2 socks. You buy a pair of Bombas socks, that's 4 socks. Because one purchased is one donated. Socks are the #1 most requested clothing item in homeless shelters. So when you buy a pair of super comfortable Bombas socks, you're also donating a pair. Bombas customers have powered over 150 million donations. So Bombas would like to thank you 150 million times. But we only have like 30 seconds. Go to bombas.com and use code AUDIO for 20% off your first purchase. That's BOMBAS.com and use code AUDIO at checkout.
Now, thyroid hormone, which is another lipid-soluble hormone, is somewhat unique. In fact, the thyroid gland synthesizes 2 thyroid hormones. They're called triiodothyronine and thyroxine. And the difference between the two is in the number of iodine atoms in their molecular structure. Triiodothyronine has 3 iodine atoms, so it's known as T3, and thyroxine has 4, so it's known as T4. 90% of the thyroid hormone produced by the thyroid gland is T4. Even though T3 and T4 are both lipid soluble, they cross the plasma membrane via carrier-mediated endocytosis. So again, they're lipid soluble, but they don't just diffuse across the bilayer like the others do. They utilize a membrane protein that binds it, engulfs it, pulls it into the cell. That's carrier-mediated endocytosis. And that's how they get into the cytoplasm. Now, even though 90% of what the thyroid produces is T4, T4 is not the active form of thyroid hormone. T3 is. So T4 has to be converted to T3 in the cytoplasm. So an enzyme that exists in the cell, that the cell's already produced, is in there and will react with T4, pulling an iodine atom off of the molecule. That will turn T4 into T3. So then, all the T3 that we've just created and the T3 that the thyroid gland had already produced as T3 can enter the nucleus, bind their receptors, and engage their target genes on the DNA. That's how thyroid hormone will have its effect. Now, sometimes the target cells need to be more or less sensitive to a hormone, so they have to adjust their sensitivity by stimulating or inhibiting the synthesis of receptors for that hormone. So when a cell increases its receptor density to be more sensitive, it's called upregulation. If a cell decreases its receptor density to become less sensitive, it's called downregulation. So that's an important thing to consider. The cell is recognizing situations where it needs to be stimulated more by a particular hormone. When that happens, the cell will synthesize more receptors for it, so it will be stimulated by as much of the hormone as it possibly can. If the cell recognizes a situation where it needs to be less sensitive to a hormone, it needs to react less, then what it can do is it can decrease its synthesis of the hormone's receptors, and then it won't be stimulated as much by that particular hormone. So once again, just to review, when we increase the number of receptors, it's called upregulation. When we decrease the number of receptors, it's called downregulation. All right, so now let's talk about the water-soluble hormone action. So the water-soluble hormones are the ones that can easily get to their target cells through the blood plasma, but then they have a hard time getting into the cell because of the phospholipid bilayer. So water-soluble or hydrophilic hormones, like peptides and catecholamines, they require the assistance of a chemical messenger in the cytosol. So the hormone itself is what we're going to call the first messenger. So hormones are chemical messengers, but we need an additional chemical messenger in the cytosol of the target cell to help get the hormone's action to take place. So since the hormone itself is called the first messenger, the assistant in the cytosol is going to be called the second messenger. So we call this mechanism of action a second messenger system. Now, you may remember this from the neurotransmitter discussions and the fact that norepinephrine as a neurotransmitter uses a second messenger system. This is very similar. So we're going to use a second messenger system for water-soluble hormones to have their action on their target cells. One common second messenger is cyclic AMP. AMP stands for adenosine monophosphate, and it's utilized by catecholamines, adrenocorticotropic hormone, the gonadotropins, thyroid stimulating hormone, parathyroid hormones, calcitonin, and glucagon. So these are the hormones that are going to utilize cyclic AMP as their second messenger. When one of these hormones stimulates a receptor on a transmembrane protein, a G protein inside the target cell is stimulated to activate another membrane protein, which is the enzyme adenylate cyclase. So let's back up for a second because that sounded a little bit different. Why did we trigger a receptor as a transmembrane protein? So the reason is because, remember, hydrophilic hormones can't get through the phospholipid bilayer. So instead, their receptors are actually on the outside of the cell. So transmembrane proteins, which act as receptors, are proteins. If you remember back from the membrane proteins discussion, transmembrane proteins are proteins in the plasma membrane that go all the way through. So they have an exposed piece in the extracellular fluid and an exposed piece in the cytosol, the intracellular fluid. They go all the way across the membrane. So the exposed piece on the outside, the part that's contacting the extracellular fluid or interstitial fluid, that piece is getting targeted by the hormone. So the hormone binds to its receptor on the outside of the cell. Once that happens, a reaction takes place that stimulates a G protein inside the target cell to activate another membrane protein, which is an enzyme. And that enzyme is called adenylate cyclase. Adenylate cyclase catalyzes a chemical reaction removing two phosphate groups from adenosine triphosphate, which you know as ATP. So if we take two phosphates from something called triphosphate, we're going to end up with something called monophosphate. So we have adenosine monophosphate, or AMP. We call it cyclic AMP because the molecular structure contains circular bonds. Cyclic AMP then acts as a catalyst activating existing enzymes in the cytoplasm called protein kinases. Active protein kinases add phosphoryl groups to other enzymes. This is a process called phosphorylation, and it can either activate or inactivate enzymes. So if we have active enzymes that are already functioning, we can turn them off by deactivating them with phosphorylation. If we have inactive enzymes that are sitting around doing nothing, we can activate them with phosphorylation. It all depends on which enzyme is being phosphorylated. The change in activity of these phosphorylated enzymes ultimately results in altering the metabolic activity of the cell. For example, when a parathyroid hormone stimulates an osteoblast, it decreases its secretion of hydroxyapatite and therefore preserves calcium and lowers bone density. We'll talk about parathyroid hormone, but I'll give you a little insight into what's actually happening. So parathyroid hormone functions to help maintain calcium homeostasis. So when your calcium levels in your blood are low, instead of depositing more calcium into your bone density, we want to liberate some of the calcium that is stored in the bones. So parathyroid hormone targets osteoblasts and stimulates them to decrease their secretion of hydroxyapatite, which is the matrix of bone tissue. Therefore, it helps preserve calcium in the bloodstream, but lowers bone density. So that's one example of what might happen there. When follicle-stimulating hormone stimulates receptors in the ovaries, it promotes the maturation of the ovarian follicles that are harboring egg cells. So follicle-stimulating hormone comes from the anterior lobe of the pituitary gland, and it targets the gonads, specifically in this example, the ovaries, and it promotes the maturation of the ovarian follicle, which is where the egg cells are being harbored. That's where they mature. So we have an excitatory reaction in follicle-stimulating hormone, and we have an inhibitory reaction in parathyroid hormone. Now, once that cyclic AMP is produced, we don't want it to keep stimulating these effects when the hormone secretion dies down. So the target cell also produces an enzyme called phosphodiesterase, and that enzyme breaks down cyclic AMP so its effects don't linger longer than we intend. So as the hormone is cleared from the system, its stimulation decreases, and there will no longer be cyclic AMP available to continue the effects because phosphodiesterase is breaking it down. Now, if we continue to stimulate the release of that hormone and make more cyclic AMP, then we can overcome the rate at which phosphodiesterase breaks it down. But if we don't, then phosphodiesterase wins and we break down the cyclic AMP and the effects stop. Now, not all water-soluble hormones are assisted by cyclic AMP and adenylate cyclase. In some cases, the G protein activates an enzyme called phospholipase, which splits the membrane's phospholipids into two different components, each of which serves as a second messenger of its own. These components are diacylglycerol, or DAG, and inositol triphosphate, or IP3. DAG activates protein kinases that eventually lead to altering the cell's metabolic activity, like cyclic AMP does. IP3 is a little bit different, though. IP3 stimulates the opening of calcium ion channels in the endoplasmic reticulum of the cell and in the plasma membrane. That allows calcium ions to diffuse down their concentration gradient from the extracellular fluid into the cytosol of the cell. Those calcium ions can then directly activate enzymes that alter metabolic activity, or they can activate protein kinases like the other second messengers do. In some cases, calcium ions themselves are also considered the second messengers. Now, the second messenger that a hormone uses depends on the target cell, not on the hormone itself. So sometimes thyroid-stimulating hormone uses cyclic AMP, and sometimes it uses DAG. Sometimes antidiuretic hormone uses cyclic AMP, and sometimes it uses IP3. It all depends on the target cell that hormone is activating or deactivating. Circulating levels of hormones are pretty low compared to other blood plasma solutes, like glucose. And this is okay because one hormone molecule can activate a large number of second messenger molecules. Each of those second messenger molecules then activates a large number of enzymes, and each of those enzymes can catalyze a large number of chemical reactions, resulting in the hormone's desired metabolic effects. So we don't need a ton of hormone floating around in the blood plasma because they have this exponential effect every time they trigger a target cell. We call this process signal amplification because that one hormone molecule, can stimulate millions of cellular products. And that means that the glands don't have to produce a ton of this hormone, and the target cell's plasma membranes don't have to be completely bombarded and overloaded with receptors just to take all that hormone up. Instead, we have this signal amplification that will maximize the effects with a small amount of hormone release necessary. All right, that is the mechanism of hormone action for both lipid-soluble hormones and water-soluble hormones. I broke it down for you in a lot of different ways, and there's definitely a bunch there. So you're going to want to review this. This is a good review because some of these test questions probably that you're going to see can get pretty hairy with these details. So maybe check out some resources on the web if you can. Check out the textbook you're using, or just Google the hormone mechanisms of water and lipid-soluble hormones and see if you find some good, reliable sources, like ones that come from .edu websites. That's probably your best bet.
You buy a pair of socks, that's 2 socks. You buy a pair of Bombas socks, that's 4 socks. Because one purchased is one donated. Socks are the #1 most requested clothing item in homeless shelters. So when you buy a pair of super comfortable Bombas socks, you're also donating a pair. Bombas customers have powered over 150 million donations. So Bombas would like to thank you 150 million times. But we only have like 30 seconds. Go to bombas.com and use code AUDIO for 20% off your first purchase. That's BOMBAS.com and use code AUDIO at checkout.
I hope that this information helps you. I hope it helps you get that B or better you need in A&P because, again, that is the goal when you want to move forward in a clinical field. So please don't forget, feel free to email me, send me your questions. I want to answer them. I want to put them on the episodes. I'll give you a mention if you don't mind. I'll just use first names. But I think that might be helpful because the questions that you have, you'd be surprised how many people probably have the same question. If you thought of it, other people are probably wondering the same thing. So we can help everybody by trying to answer those questions. Again, thank you so much for listening. I really appreciate all of the support, and I look forward to seeing you next time. Anatomy and Physiology Bit by Bit is a production of Minus 55 Media. Please take the time to rate the podcast, and don't forget to check out my YouTube channel, Student Help for AP. That's Student Help, the number 4, AP. There's a whole lot of tutor videos on there that I think you're going to find helpful. Special thanks to my family, Bucks County Community College, and McGraw-Hill Education, where you can find Anatomy and Physiology Digital Suite, my low-cost, tutor video-based digital learning solution for anatomy and physiology, already being used at several colleges and universities.